Let's consider the constant strain triangle as a good example of an element that we can use to derive the stiffness matrix from equilibrium and to learn about assembly and to show some applications and some problems. In the 1950s, the aircraft industry needed better methods for analyzing structures. One of the most critical needs was in aeroelasticity. Both for static and dynamic aeroelasticity, such as flutter, you need a powerful method that lets you study the complexity of the structure and then allows the dynamics. Wing and much of the fuselage structure is made of thin metal, and membrane analysis is often common. For that reason, the first two elements to be widely used were the membrane triangle and rectangle. It was a group at Boeing led by Turner with Martin, Clough, and Top that published the first paper on that topic in 1956 in the Journal of Aeronautical Sciences. And that really was probably the most important paper in starting off the finite element revolution in structural mechanics. Before we look at the theory for the constant strain triangle, we'd better review a little bit of elasticity because I think some of the viewers might be a little bit rusty. In this figure we show three of the classical vectors that are needed: the stress, the strain, and the displacement vectors. These are related through matrices. The first here is a strain displacement law, and the other is the stress-strain law, sometimes called the constitutive law. And this one here, the so-called G matrix, which you might remember as generalized Hooke's law, is purely a material characteristic. The strain displacement law with symbol D is purely a geometric property. And so in mechanics, people separate those two roles rather cleanly. Notice that there's a 6 vector of stresses and there's a 6 vector of strains, but there are only 3 field displacements in the 3 coordinate directions. Typically you think of a Cartesian underlying coordinate system. So there's a little bit of a problem if you try to specify the strains and then recover the displacement field. This is a question of integrability. Elasticians call this compatibility or displacement compatibility. And we're going to bump into that in this Turner triangle that we'll study because the starting point there was to assume constant strains and to try to recover the displacement field. From this problem on, however, we will move into energy methods where the reverse approach is taken, where you assume a displacement field and then you're not caught on the compatibility question after this. Equilibrium is another law that we need to follow, which must hold throughout the interior of this potato-shaped elastic element. And then the boundary conditions around the periphery. All told, this becomes a boundary value problem in 3 dimensions, as it's described here. So, if we move to 2 dimensions, then the problem simplifies. We have a 3 vector for stress, a 3 vector for strain, and a 2 vector for displacement. Our matrices are still given the symbols D and G that relate those quantities. We still have compatibility and equilibrium that have to be called upon, and boundary conditions. But in this case, rather than a potato-shaped body, we have a potato chip, where the H dimension, for instance in plane stress, is quite small. Now, conversely though, plane strain can be very thick through that dimension, and a common example called out is a civil engineering one where you have a dam perhaps spanning a valley between 2 mountains, and the dam is a straight dam with uniform cross-section and it's perfectly confined at the ends. Whether you're dealing with the thin or the very, very thick body like that, in 2 dimensions. What it means is that the third dimension is somewhat trivial. Either nothing happens in that direction, or whatever happens can be figured out from the other 2 dimensions. And so the problem basically reduces to solving a boundary value problem in the plane, typically of the xy coordinates, as mentioned here. So this is the kind of problem we have for our Turner triangle. Now I will explicitly show the mappings for the plane stress problem. Here's the G matrix. It involves the material properties, Young's modulus, Poisson's ratio, and the shear modulus. Now the shear modulus is not independent. It actually can be found from the other 2. So we often write G is E over 2 times 1 plus nu. And therefore, if you're given 2 of the 3 quantities, that's sufficient. Some of the finite element codes even call it an error if you try to read in all 3, since numerically they're so tightly related. Then the strain displacement law is shown here, and it's the relation that's 3 equations and 2 unknowns. So you can see why that's a little bit of a problem when we want to invert that. These are derivatives involved in this operator, whereas these were algebraic constants up above. And so the 2 relations are rather different mathematically. When you want to deal with the material law, then it's an algebraic transformation. When you want to deal with the strain displacement law, you're either differentiating or integrating. Let's now go through the derivation of the stiffness for the Turner triangle. This will involve some mathematics and might bore some people at the outset here. If you are bored, skip ahead to the final results, the final statement of the stiffness, which is in the next scene, and then maybe look at some of the problems. You may want to come back and fill this math in at some time when you're comfortable with it, because it has historical significance. And although it's a little tedious, it is pretty straightforward. We start out with the necessary relations between the variables involved. For some years I've been teaching with these 5 vector variables displayed in the pattern that they are shown here. The nodal displacements on the right, which really govern everything in the problem in the method that we ultimately develop here. Then the field displacements, which are given with italic symbols, and differentiate them from the upright symbols or the Roman letters here on the nodal displacements. The strains are 3 in number, the direct strains and the shearing strain. Likewise the stresses. And then on the left I've put the 6 nodal forces. And the real goal of developing a finite element is to bridge this gap all the way from the nodal displacements on the right to the nodal forces on the left. The classic theory occupies the middle ground with the relations as shown, with the strain displacement and the stress strain law. Then we must fill in this equilibrium approach, the missing geometric law over here on the right, shown with a question mark, and then the equilibrium law on the left, also shown with a question mark. Now typically, especially in more complicated elements, you cannot find this operator here. The reason is that statically indeterminate structures don't let the user guess very well how the force at a node is distributed into the interior of the element. Now luckily on this simplest of 2-dimensional elements, this constant strain triangle, we can guess how that works. So we make it in this case. And then if we can put together this total mapping from end to end, we would have, once grouped, enough matrix operators to form what we call the stiffness matrix, which is the sum total relation between the nodal displacements and the nodal forces. The way that we will develop the relation between nodal forces and internal stresses is through an artifice of looking at a uniform rectangular sheet under uniform stress. If we imagine that that sheet has inscribed in it this dashed line that shows a triangle, then really the entire sheet is in uniform stress under this sigma y stress, say. We can do the sigma x and the shear stress later and then superpose results. But for this uniform stretching of the sheet then, if we can infer how the triangle is acted upon by these forces and how those forces ultimately can be lumped at the points or the vertices of this triangle, then we've got a good start at the force equilibrium of the element. So let's create some free bodies here in this diagram. Consider it an exploded view and concentrate on this upper left body first. There is this stress along the top edge. We're going to try to equilibrate it with a force that will be transferred to our proposed constant strain triangle. If you sum those stresses through the thickness h and account for the distance here, x3 minus x1, you get this total force. We're going to then assume that that is acting here and is opposed by this force on the element itself. So it's a rather complex way of resolving this set of distributed stresses into this concentrated force at the mid-side of that finite element. Then we do the same thing for these other stress fields, and it's a way of lumping the given distributed field into a concentrated force on the mid-side of each side of the element. Now those lump forces we can imagine at the mid-side of the element. And furthermore, we can break each of those into half and move half to each of the nearby nodes as shown here. That's a statically equivalent representation of those loads, so in that way it's good. Then the magnitudes of each of these loads will be proportional, of course, to the amount of exposed area on the original rectangular sheet of material. Let's look at that summation of forces, say, at a typical node such as the one on the right here, to get the force F4. When we do that, the vertical upward component was due to the exposed stress at the top, sigma y times h times the running x distance, which is x2 minus x3, and that's a positive amount. Likewise, the vertical component pointing downward is sigma y times h, and then the exposed distance x2 minus x1, where the minus sign carries the fact that it's pointed downward. When you add those two together, the x2's cancel, and then you get this expression. Numerically, that will be negative because x3 is larger than x1. But then that makes sense. Now we can do a similar process with the other components. What we'll do is make up a matrix that we know needs to have this form, a 6 by 3 matrix relating the 6 nodal forces to the 3 internal stresses. And what we've just done is to concentrate on what would happen with the sigma y applied stresses. Now that will give you typically this column in the middle if you can find all of those terms. We did find this term, which I'm using a compact notation on, that the x13 actually equals x1 minus x3. That in fact is a negative term, as you might guess, because there was more surface area exposed at the bottom of that sheet metal than there was at the top. And so F4 in fact will algebraically come out negative in this case. Likewise, F3 can be determined to be 0. That would be the horizontal component at that node. By summing the other forces at the top and the, let's see, in the left nodes, then you could get these two terms here and these down here. And you could fill out the whole matrix that way. And I've done that process in the problem number 5 at the end of our lecture. That completes our study of the equilibrium law, which, as I'd mentioned, we're lucky to be able to derive. But now let's go to the displacement relation that we needed. The assumption of constant strain allows us to put numbers in for the strain vector, and we'll use little a, b, and c. Those were related to the field displacement by that differential law. We'd like to map in this direction, though, and so that will require integration this time rather than differentiation. And also brings up the specter of displacement compatibility, because there are three equations in two unknowns. And in general, this would not be integrable. Then we need one remaining matrix here, which I've been calling sort of a displacement relation. It is between the field displacements and the nodal displacements. In modern methods, there's a way of doing this that's automated and involves functions that are called shape functions, which we'll get to in later lectures. But for the moment, we have to be satisfied with this one-of-a-kind solution using equilibrium, because that was a historical process. So we're going to need to integrate this relation, that these strains here are related through the D matrix to the field displacements U. Then after that, we're going to use a trick to find the relation in this direction here, and we'll initially get the relation in that backwards, you might say, relation direction, so we'll have to invert that matrix when we finally get it. The first of those three equations in two unknowns was for the strain epsilon x, and showed how to integrate that in the x direction. We have this equation that results. We'll use a for the symbol for epsilon as a known quantity. Now really, when you've got a derivative given and you're trying to recover the function, it's really the fundamental theorem of calculus that says that the function then is the antiderivative or the integral plus an integration constant. Now for us in partial derivatives, the y variable is being carried as if it were a constant, and so what was once a constant of integration becomes an arbitrary function of y. So we'll carry that on here with the symbol f. We can do the integration and get ax as the indefinite part of the integral there. So we can do the same thing with the strain in the y direction through that strain displacement law. Integrate the displacement field to be by plus an arbitrary function of x. We'll give it the symbol g. Our major worry now is whether we can find a g and an f that will satisfy the strain equation, which is the third relation. Can we get a unique displacement field? In general, you cannot. And our third equation is going to require this relation. So we don't try to integrate it, but rather we put our solutions for ux and uy in here, namely these two solutions, and then carry out the derivatives and find this relation. This is sort of a check now, and it really is it's a version of a compatibility relation. But how can you have a constant equal to something that might be a function of y and then added to something that's a function of x? The only answer is when all three of these things are separately constants. And if that's the case, then let's just call the second one here, the intermediate one, call it a, and then the one on the right is forced to be c minus a, and you get basically an identity here. So we're okay to this point. Let's now evaluate those arbitrary functions that entered the solution. F of y has to obey this differential law, and we can integrate that directly. That introduces another constant of integration, capital B. G of x we can integrate directly to bring in this polynomial with a new constant c. To interpret these capital letter coefficients a, b, and c, we can insert those into the equations for the horizontal and the vertical motion of the body. And after doing that, we see that the terms ay plus b are here on the x motion, and b becomes a rigid body mode to the right. The reason being that it represents a constant x displacement over the face of the element. So the element that was originally here moves uniformly over here with amplitude capital B. Likewise, the coefficient c becomes rigid body motion upward because it's a constant y displacement value. The coefficient a, capital A, is a little more complicated. It's harder to see, but also is a rigid body motion, but a rotation. And you can see that by looking at the horizontal displacement field, which as you go in the y direction becomes larger in a linear way. In other words, if there's a straight side on a body, which might be rectangular to start, and as you move up along the edge, you find that the body is moving in this way with increasing displacement. It looks like a rotation about the origin of that face. Likewise, if you take a face that's horizontal, then you find that the minus ax term here says that there's a rotation in this direction, downward, with the displacement field increasing as you go that way. Well, those ideas are also easy to see in a matrix form where we separate out the generalized coordinates, so-called, to the right, including our original assumption on the A, B, and C, the small characters, and then the newly found rigid body modes, cap A, B, and C. This form of a displacement matrix is useful because it brings out then the modal character of these different kinds of motion. In other words, those two rigid body modes, B and C, multiply these columns at the back. The rigid body rotation multiplies this column. And then the straining modes are the ones here, and the constant strain in the x direction, and then the y, and then the shear strain. So it's a convenient way to look at the problem, and often if you can find these so-called displacement functions or this displacement function matrix, it's easy to discuss the overall displacement field. So we have successfully integrated the field displacement, and we know what it is, but yet we haven't tied that to the nodal coordinates, so that will be our next job. What has happened is that we've identified an intermediate matrix, which I'm calling generalized coordinates, and we know how to map from the field displacement to them, and we've called that new displacement function matrix phi. So there's a new kid on the block. But we're still missing a sub-matrix now, still labeled with a question mark, another question mark, to eventually connect us to the nodal displacements. We'll call this intermediate vector Q, and if only we could get this last chasm hurdled here, we would have our full mathematical form of the stiffness matrix. Well, that's done by a trick. What you do is you recognize that the field displacement becomes identical with the nodal displacement when you put in the coordinates of a given node. And that's easily done. For instance, in this first equation here, I take the field displacement u of x, that's the x component of the way that the body is moving, and then evaluate it at the coordinates of the first node, x1 and y1, and that's identically the nodal coordinates, what we mean by the nodal coordinate u1. But here's where I take the field variables and put in the x1 and the y1. Then I do the same at the first node where I look at the y component of displacement, and that's what we call u2. And we evaluate that, and so on. And you'll get a total of 6 such equations. So we put these 6 equations in 6 unknowns into a matrix form, and the generalized coordinates naturally fall out of the backside here as a vector, and then the nodal coordinates to the left here. And this is a natural mapping in this direction, which is not the direction we really want. We'd like to get it the other way around. We'd like to get the nodal coordinates on the right-hand side mapping into the generalized coordinates. This can be done, I've shown it symbolically as H inverse, and this can now be done by programs such as Mathematica and Maple that are symbolic language programs and can manipulate symbols. In the old days, these kind of symbolic inversions were one of the hardest parts of the finite element problem, and that carries into the energy methods too if you ever have to do those inversions. We have all of the mappings that are needed now. We have the equilibrium law, this displacement function matrix, and this H matrix, which we don't give a name to particularly, except that it is a relation between the nodal coordinates and the generalized coordinates. And if we do indeed map from one end to the other with this kind of a relation, then we identify the stiffness matrix as the composite product of all those mappings and define that as our equilibrium form of stiffness. In the original work by Turner and his co-authors, it was found easier to develop the stiffness matrix if you used an element coordinate system, which was a special coordinate system aligned with the bottom edge of the triangle. And then you make the y-axis pass through the vertex of the triangle. You can see what happens quickly here, namely that you get zeros in 3 of the 6 coordinates that are important, and then that knocks out a lot of the terms in those matrices that we were just talking about. So this shorthand notation is nice. This x21 is x2 minus x1, and we can write out the matrix then in these element coordinates for you. Here's the first part of the stiffness matrix. It's due to the direct strains, and it has a vertical column, interestingly here, that is all zeros, and a horizontal one that's all zeros. So there's a little bit of uncoupling of a certain kind. That special coordinate system makes that true. Luckily, that happens because it makes some homework problems a little easier to do. In any event, I'm going to call out the stiffness matrix K as a sum of this term of components involving Young's modulus plus some terms due to shear in the next figure. The second matrix due to shear effects is shown here, and again with a nice column of zeros and a row of zeros. What this means really is that there's just a fortunate effect that when you use that special element coordinate system, that the displacements at the point up here at this vertex are rather sensitive to the difference between direct stresses and shear stresses. And this will come out a bit in a couple problems that I'll do later in the problem session. Finding the stiffness matrix is perhaps the greatest single achievement for a finite element. Then a second one that we'll get into later in later lectures has to do with how one redistributes loads on the body that originally distributed loads such as gravity. But possibly the third most important point is the assembly of the elements and how they can be connected one to another. And that's what we're going to study now. In this figure we have a deep beam. Let's presume it's in plane stress, and we'd like to show how it might be assembled from 3 finite elements as shown here. I don't want to say this is a good model. In fact, it's a very poor model. We'll discuss that in a minute. But for now, we'd like to know, how do you connect these points to the neighboring points? And how do they merge together into a matrix that would be the system matrix? Well, we can identify that in plane stress, say, that this problem would have 10 degrees of freedom because there are 2 degrees of freedom at each of 5 nodes. So we would form a larger 10 by 10 matrix shown here. Then we would look at the different elements. For instance, the left one denoted with alpha and red colors connects 1 and 2, 3 and 4, and 9 and 10, remembering that that element is a conductor of force between all the nodes to which it's connected. So I can block these out, that the grid point 1 is connected to, in turn, 2, 3, and 4, and then 9 and 10. Likewise, grid point 2 is connected to 2, 3, and 4, 9, and 10. So these alphas represent non-zero terms that the first element contributes. Then the beta terms would do likewise. They would come in connecting 3, 4, 5, 6, 9, and 10. So we could come in and draw our little beta and overlap here on these remaining locations. Now I'm going to get tired of this pretty quick, I'll tell you, but let me do a handful. Then I'll block out the rest. Okay, and then there would be others in here. And they would just superpose, as we saw earlier with the line element. And then there would be another block lying here and a block lying here. Now lastly, you would have the green components here, and these would contribute to 5, 6, 7, 8, 9, and 10. And why don't I just block that out? 5, 6, 7, 8, 9, and 10 will give me this block here with lots of little gammas in there. Well, you can see how the overlapping goes. Let's now exploit the fact that the connectivity in the stiffness matrix really doesn't depend on the individual degrees of freedom, but rather it goes node by node. Individual stiffness matrices tend to be full, and it turns out that every degree of freedom at one node is typically affected by every degree of freedom at another node. So what you can do is use compact notation, where you condense down the amount of information to only the nodal numbers and only keep track of which nodes are connected to which other nodes. So when you do that, you introduce symbols such as the force symbol here, which really in our two-dimensional problem is a 2 vector. The symbols for stiffness are really 2 by 2 matrices, and the displacement over here is really a 2 vector. That lets you draw the earlier problem in this simpler form with a nodal numbering only, and we can quickly account for the connectivities. The alpha terms given in red are shown in the matrix and connecting degrees of freedom 1, 2, and 5. And so they appear in these locations of K11, K12, K15, K21, K22, K25, K51, 52, and 55. Beta likewise connects 2, 3, and 5 and appears as these blue symbols here. Lastly, the gamma shows up in the green symbols connecting 3, 4, and 5 and is concentrated pretty much in the lower right-hand box of that set of terms. Well, we've had some luck in finding a stiffness matrix for a moderately sophisticated element and learning how to assemble. We learned that the elements were conductors of force, and we showed how they could assemble into a stiffness matrix for the total system by connecting node points. I didn't mention the inter-element boundaries, but those should be viewed as welds, just as the grid points themselves should be viewed, first of all, as if they're welded together. Now we're able to force the displacement compatibility and force equilibrium at the nodes. It's a little less obvious whether you can hold those inter-element boundaries between the elements fixed together or not. Many elements do, and those are called conforming elements, but there are some that don't, in fact, that are called non-conforming. Generally, it's better, though, if they are of a kind that appears as if the edges are welded, because you don't want enormous holes opening up or overlapping material. So it's usually a goal to treat that inner element boundary as a weld. I'd like to finish with a little comment about the model that we've used for the deep beam. It's really pretty bad to use a constant strain element through the depth of a situation in which there's any bending occurring, because bending, you know, requires a reversal of a stress through the thickness of a beam. You know, the top fiber will be in compression, say, and the bottom in tension. And the constant strain triangle cannot do that. And so problems that are posed with these constant strain triangles have to have many, many small elements. And it turns out the convergence is not real good on this element. So it's not used an awfully lot today in really day-to-day practical work. That constant strain effect is a little bit like an inclusion in a problem in a continuum where you freeze something over a region. It has to all be the same. And a little like finding a raisin in your porridge, I guess. There it is, and it's a lump right there. And so people don't use the constant strain triangle so much for practical work. But nevertheless, it's a very good intuitive tool, and historically was the first really practical finite element that was developed. Now it's time to have a problem session. We want to look at some of the ideas that we learned in the lecture and convert those into practice. I'll start out with the easier problems and work toward the harder. The first one's an assembly. Suppose you have 3 triangles stacked up like this and then welded at the corners. The first triangle, which will be represented by little red triangles as its stiffness contribution, connects nodes 1, 2, and 4 in this compact notation. And then respectively the others connect 2, 3, and 5, and 4, 5, and 6. So since there are those 6 nodes to be considered, we would make a stiffness matrix that would be 6 by 6 in this compact notation. And then we would embed these various symbols into that. The triangles that connected 1, 2, and 4 are distributed as you would now expect, conducting force between all those coordinates. The lower left element used a little blue square which connects 2, 3, and 5, 2, 3, and then jumps over 4 and 5. So it's got this little blocked out pattern too. You can start to get a feeling for the connectivity and the way elements contribute. Then lastly, the lower right triangle connects 4, 5, and 6, which is a block in the lower right here. So you do develop these patterns, and of course if we were dealing with real element assembly, we would be using numbers in these positions, and they would be different. Most of the stiffness matrices for individual elements are full matrices. That every degree of freedom affects every other degree of freedom in the element. You might get an occasional 0, but more often than not, elements are rather interconnected within their own boundaries. Problem 2 is a deep beam model with 2 triangular elements, a plane strain model. Again, it's a rather weak model because of the poor stress field within the constant strain element that we have developed. The equation of equilibrium shown here has both unknown forces and displacements, but there are also known forces and displacement sprinkled in there, and those should be identified at the outset of the problem. I'll call those boundary conditions. Later on, some of them become in the interior of the problem. But a common idea is that you must specify one or the other in each of the degrees of freedom all the way down through the set of the equations. The reason being that there are n equations here, but there are 2n forces and unknowns. So we have to specify half of them, and learning how to do that is an important part of problem solving. If you don't specify in the common finite element codes, then you will be given zero force as the default. And there would be typically 4 combinations possible of either zero or non-zero, force or displacement. And so you have to know how this is done. The first thing I'll do is fill in the remaining degrees of freedom, numbering nodes 3 and 4, and then I'll write down the general vector forms over here. Now what do we know? Well, at the wall we know that there can be no displacements, u1, 2, 3, and 4. So we put zeros in these 4 locations over here. Can we say anything about u5, u6, u7, and u8? No, those are going to be determined by the problem. Those are the unknowns, really. But conversely, we don't know the forces at the wall, so we can't say anything about them. So we'll just let those write as symbols. But we really do know all 4 force components that are in these 4 tip coordinate directions. Namely, the vertical force here, that was given to be 1,000 newtons down, so we'll put that over here. We know that there are 0 forces on these other coordinate directions, and so we get 3 other zeros. Now, the fact that forces are so 0 happens so often, it turns out that that's the thing that's taken by default in finite element codes. So when I said earlier that the user had to specify one or the other, that's true in theory, but in practice, the computer codes uniformly assume that if you forget to say which one has either a 0 or a non-trivial value, then the computer code will put a 0 in for the force. And it turns out that that's 90% of the case. So, so in the interior of the body, generally the forces, the live loads are 0. An exception would be if you have gravitational forces, so maybe in some civil applications that wouldn't really be true. But in most mechanical, aeronautical applications at the component level, we have 0 applied forces through a lot of the structure. Problem 3 is an equilibrium solution for the deflection of a simple structure. It's rather idealized in that I've taken this triangle and we're going to apply a load at the tip, and I'm going to suggest that a single constant strain triangle be used to analyze it. Now that's really, of course, an academic exercise. One reason that a single triangle wouldn't do so well is that the single constant strain triangle moves with straight sides. It turns out that's all it can do. That's useful when it's joining other elements nearby, because then it is a conforming element with its neighbors. But if there are no elements on the sides, then you might have expected it instead to have bowed in a little bit here, kind of pooched in through a Poisson ratio effect. But this element cannot do that. Now the element is 200 millimeters on a side, it's 10 millimeters thick, and it has this Young's modulus and Poisson's ratio. So we're going to be able to calculate all the physical coefficients in the stiffness matrix and actually get a solution. In our solution, one of the first things to do is establish a coordinate system and then number the nodes. So we'll put our coordinate system as the special one for element coordinates that works so well, passing through the vertex. We'll number our nodes 1, 2, and 3. We have to calculate the altitude of that triangle because the coordinate y3 enters the stiffness, and that's 173 millimeters, just using the sine of the angle here, which is some 60 degrees. And our set of equations then is like this, that since this is a clamped node and the one over here is clamped, we're going to have 4 zeros there. We don't know the forces corresponding, and that's okay. Those are reaction forces. But these 4 here allow us to forget about the first 4 columns in the stiffness matrix. They won't enter because those terms will be multiplied by 0. So we're left really with a block of 2 equations and 2 unknowns down on the lower right here, and then we can partition off the upper set of 4 equations and set them aside for later. And that's uniformly done with solution methods in finite elements, because you may not want those reactions, and typically in finite element code you have to ask if you want those reactions found later. Well, in this case, because of the symmetry of the elements and because of that nice coordinate system, we get a complete uncoupling, and we find that the 5th coordinate, which is the horizontal one, will have a coefficient times u5 equals 0. And I show that in the next figure. So that equation yields u5 equals 0. In other words, the tip of the triangular structure doesn't move right or left. Well, that makes sense because of the symmetry of the load. Then the 6th, or the bottom equation there, works out in terms of Young's modulus, the thickness of the sheet, the coordinate x21, which is really the difference x2 minus x1, which is 200 millimeters, and Poisson's ratio of 0.3, and the y3 that we had, which was 173 millimeters. So you solve for u6 in terms of those quantities, and you get 0.00076 millimeters. Now, I'm not really justified to carry even 2 significant figures, because probably the correct answer there would be half again or twice as much, because our little element will be way too stiff. This would be a fun problem for someone to actually mash on a preprocessor and solve and see how much greater and more accurate answer would be. There would always be a little singularity right at the tip. You'd have to blunt the tip on a little bit so that you didn't get an infinite stress right at that point. And an interesting side observation is that the element solution that we've done, the single element solution, doesn't have any shear deformation or shear modulus entering into the solution. Problem 4 deals with a bracket made in a triangular form. We'll make a simple problem of it again and model it with just one finite element. This is a right triangle and with a load downward at the tip. Again, I'll take 10 millimeters thick, as in our problem 3. We'll make this 100 millimeters on a side. Young's modulus, Poisson's ratio, and we'll calculate the shear modulus ahead of time, and it works out to be that. In our solution, we first establish a coordinate system at the lower left corner, and then we number the nodes as 1 and 2 and 3 with the corresponding degrees of freedom. Then we have the standard element coordinate system that Turner used. We are constraining the 2 nodes at the wall to not move, and that's why when we set up our 6x6 set of equations here, we constrain the first 2 degrees of freedom and the last 2, the wall degrees of freedom, and then they have corresponding unknown reactions at this point. Meanwhile, the tip is free to move. It has the, so we don't know the displacements, but we do know there's no horizontal force, and there is a minus 1,000 Newton downward force. And so we have a 2x2 problem that results from this. Really, the logic is, if I go through it carefully, that these zeros will cancel out column-wise these 2 columns. This 0, this one, and this 0, this. Because post-multiplication by a component of a vector like this acts column-wise. Then, to eliminate the first couple equations and the last couple, you really are partitioning out equations. You're not canceling them or forgetting them, but you're merely setting them aside. And then those are used to find the